So let's study how to represent the floating point numbers in computing system. So a floating point number is the representation of a real numbers. A real number means the value with the fraction part. So far we have studied signed magnitude, one's a complement, two's a complement, and then excess m notation for signed integer. But without modification, these formats are not practical to represent a value with a fraction part, a real number. And in computing system, the real number in math is represented by floating point representation. Here, the term floating point is that when you have a fraction part, you write some digit and then pointer, radix pointer, and then some digits are there. And this point is not fixed. Depending on the value, the point is moving around and floating around. Based on that, we call this as a floating point representation, which is intended to represent the real numbers in math. From the observation that we write floating point numbers or real numbers with this kind of notation. Also, we have another notation called scientific notation. So scientific notation is we have some value, and then using a power of 10 we express exponent. So something times a power of 10 with the exponent, you can represent any real number. Something like this, 5 million, we could say 5.0 times a power of 10 and the exponent 6. So in a computing system, a floating point representation is based on this scientific notation. So the very basic idea from the observation, we find that three components are in scientific notation. First, sign. Second part is a mantissa, and then exponent part. So power of 10 is assumed. So by representing sign, mantissa, and exponent in binary number, we can represent any number, any real number in computing system. So here we give a certain number of bits for each component of sign part with a plus and minus only, so one bit is sufficient, 0 for positive, 1 for negative. And exponent, so to express the exponent we need to assign certain number of bits. And then significant. So significant mantissa here, as you have a footnote, significant mantissa are not technically the same, but we use interchangeably. So from now on, we are going to use the term significant. So by representing this way, the value is actually sign plus or minus, and then significant specified here times a power of 10 is assumed, and then exponent of whatever value given here. So in a binary number representation for floating point real number in computing system, so we need to decide how many bits we want to allow for exponent part, how many bits for significant part. That determines the range of the numbers that can be represented, and then accuracy of the numbers it could represent. So here it's a recapture of that. So we assign one bit for sign, and then we assign certain number of bits for exponent, and then certain number of bits are significant. So out of those three components, we can represent a number with a fraction part, and that is called the floating point representation. There's a standard format for floating point representation. So the institution named IEEE has established a standard. It has two standards. One is a single precision, another is a double precision. So the standard number is a 754, and single precision uses 32 bits to represent a real number with a fraction value. So it has 1 bit for sign, and then 8-bit for exponent part, and then it uses excess 127 representation, and then significant part we have 23 bits. So total this is a 31 plus 1, which is sign, so 32 bit. And the double precision we use double the number of bits. So in exponent part, we use 11 bit and with a bias of 1023. So excess 1023 signed integer representation is done in exponent, and then 52 bit for significant part. So here you have 63 bits plus 1, which is a sign, so we have a total 64 bits. So how IEEE single precision or double precision standard is used? Here is one thing you need to remember is that when you represent the significant part is something like 0.12, and then you have some exponent part there. So in significant part, always change this value by adjusting the exponent, having the leftover radius point should be always 1. So we do not allow 0. This part should be always 1. There should not be any more than 1. So just 1 only. So 1 point whatever is required. That's called normalization though. So by adjusting the exponent, you can do that. If I have a 0.12 10 to the second power, then we can adjust this way 1.2 times into the 1. So by applying 10, so you can just reduce exponent, something like that. So you can always adjust the exponent to have the whole part is always 1. Of course, this is a decimal representation, but in binary representation, same thing. So for example, if you want to represent the 4.5 as a decimal value, but in IEEE format, first we need to convert it to binary value first. So 4.5, 4 is 100 in binary, and 0.5 is 1. So the first position is 2 to the negative 1, which is half. So this is a binary representation of 4.5, but we need to normalize such that we will have only 1 point something. So we can change this one 1.001. Then we need to multiply a power of 2, since we move the point 1 to twice. So it should be a power of 2. So very similarly, in decimal number, we use a 10 here. So recall that suppose I have a 234.5, then this is equivalent to 2.345. Since we are moving this decimal point in 2 positions, then here we can have a power of 2 with exponent 2, this is equivalent. But since this is binary number, well, power base is always 2. So we have this value set, and then we represent this value in IEEE standard format. So always remember that the significant part should be 1 point whatever, and then adjust the exponent by doing so. And this process is called the normalization process. So let's take a look at real example for doing so. Suppose we have a negative 3.75 in decimal number. Then let's represent it in IEEE single precision. So first step is to convert this decimal number into binary. So negative 3.75, so whole part is 11. 0.75 fraction part is 0.11. So combined together we have this one. So you can use the division method for whole part, multiplication method for the fraction part. So conversion is done. And second, we need to normalize. Since we cannot allow 2 ones, we should have only 1 1. And then in this process, we move the radix point to the left by 1. Then we need to have exponent 1 coming here. So this is a normalized form for IEEE floating point representation. Then what you do in IEEE a single precision is we have 8-bit exponent, and then we have a 23 significant, and then one sign bit. Since this is negative number, sign bit should be 1, and this one is exponent 1. But in exponent part, we use excess 123 notation. So 1 and then excess bias should be added. So 128 should be in this part. So 128 in binary number is 1000000. That's 128. So 128 is actually 2 to the 7th power. So 0, 1, 2, 3, 4, 5, 6, 7. Seventh bit is a 1. So that's the exponent part, excess 123. And then significant part is this portion is a significant. Remember that 1 point, 1 is always implied. So we never represent the directly insignificant, only the after the radix point only. So we have 1, 1, 1 and all zeros. So that's how to represent the given decimal value into IEEE floating point representation for single precision. And then let's do the reverse way. Suppose we have this IEEE single precision floating point representation. What is the decimal value for that? So first, sign bit is 1, so it should be negative value. And then exponent, so what the value is being represented is in decimal value it's 128, since this is to this 7 value. So 128 is there, but we know in exponent it is excess 127. So 128 when the bias excess 127, so which is actually 1 is there. So this part is exponent, so exponent is 1. So the value being represented is something like this, minus and significant we are going to find. The significant is 111, and then in IEEE 1 point is always implied, and then 111 is only fraction part. And times exponent, the base is always 2, and then exponent as you compute it is 1. So that's the value being represented by this one. And then this one is equivalent to 2. If we multiply 2, it's a 11.11. Of course, negative. Then whole part is 3. Fraction part is 7.5. So this representation expresses a negative 3.75 in decimal value.